So it's a good idea because on this subject I could probably talk for days. It's really a huge. I mean, I'm going to concentrate on things from the last couple of years, but just to set the ground. Why is Avi saying what he said? Why am I saying that it's such a huge thing? So I don't. First of all, you can easily do a semester-long class on planar graphs and without boring it. So there's so many or about these things. Somehow, it's a lost art. I don't know if you know this, the Haywood problem, on which the complete graph. We know that in the plane we can embed K4, K5 we cannot. If I tell you Kn, find me the lowest genus in which Kn can be embedded. It's very easy to get a bound on this. So I'm now forgetting if it's a lower and upper bound, but from Euler's formula. But it is possible to find an embedding that meets it, that matches it. And that's very complicated. This is work from the late 60s.
That's more topology than theorem.
No, it's combinatorics.
No, of course, but it's related.
Yeah, absolutely. So it's really endless. There is a Kebbel-Drell-Thurston theorem that says that every planar graph can be realized as the touching graph of disks in a plane. Deep and beautiful theorem. And there is separator theorem. It's really endless. So there is in fact a book. I taught a class. And I didn't even cover half the book. Novas has a book from about 2-3 years ago.
Amazing.
More or less,
Unbelievable. Yeah, so
it's an amazing
like
guy.
all of them,
He writes amazing books. So with almost the same title, I forget exactly. Graphs in geometry.
Geometric representations of graphs.
No, that was the name in the past. Now it's called something different. I forget. So it's really endless. Just one more thing to mention. I don't know, I'm trying to see, not everyone knows this. So let me just say, just as to give you a sense of another aspect of this. So there is a theorem of Bourgain from the 80s, which says that every endpoint space by the way, we are few enough and feel free to don't wait till the end. Avi has already given you the right.
No, people will ask you what they don't know, and if they don't, Leo will ask.
Okay, the endpoint metric space embeds with distortion. Not a hard proof, but very clever proof.
What is distortion?
So this means, for example, okay, so this means you have, that's the metric space endpoints. So you can map it into L2, in fact, into Rn is enough into L2, such that for every x and y in X, now you'll have something like the phi of x minus phi of y. This is larger than or equal to xy, and less than or equal, less than or equal the constant order log n times the.
This is distorted by math.
Okay. And what together with Nolan and Rabinovich, we prove this is type G for expanders, for bounded degree expanders. So what this theorem says is that the graphs, the metrics of expanders are as far as possible, essentially as far as possible from being Euclidean. Okay. So geometry and graphs really interact in many ways, also algorithmically. You know, one of the first things that one learns in data structures, algorithms class, is how to compute distances in a graph efficiently and so on and so forth. So there's really many things like this that. So the connection between the two for me is completely obvious and very rich. So one thing which, to my shame, I found out only quite recently is that there was a person, Oystein Oren, he was in Yale, Norwegian. He was very influential. I'm afraid he's also, people don't know him. He wrote one of the modern books in graph theory, and he made the following very beautiful, very natural definition. He says that graph G, geodetic, if for every two vertices, in G, there is a unique shortest path. So between, there is a unique shortest path.
The graph is weighted.
No. This is unit. Okay, so let me, since you're allowed to ask me, I'll ask you. Can you find examples like this? Give me examples. Please. Okay, very good. But three, in a way, it's a correct answer. But this is really not very satisfying because the paths are unique, so there is really no competition.
Odd cycle, very good. Okay. Anything else? There is something. This guy, which we will encounter today again, Pettersen. So let's talk about Pettersen. That's one of the things that in kindergarten graph theorists are taught. If you have a conjecture on graphs, always test it on Pettersen. You have a good chance to refute your wrong conjectures. What's special about it? It's special in many different ways. Let me just to give a description. By the way, I was once sitting in a cafe in San Francisco working, and I was drawing, and somebody approached me and asked if I'm involved in black magic. Correct story that we have this correct story that really happened. So let me give you a description.
Yes.
Of course, what else are we not? How involved in anything else? So that's our profession. So if you want the description of this graph, mathematical description, just a drawing, it has 5 choose 2, 10 vertices, which correspond to all the pairs out of 1 through 5. And adjacency means that the 2 pairs are disjoint. That's the description. But in addition, this graph has diameter 2 and girth 5. So the shortest side of this graph has length 5, which means, let me tell you these 2 facts in different words. Every 2 vertices either are adjacent, there is an edge between them, or there is a unique path of length 2 that connects them. So in particular, of course, it's good. Okay, so the supply of such graphs is quite limited. And in fact, so I'm interested, there is literature on this, definitely at least 20 papers written. So this is, by the way, I didn't say this. This is, he made this definition in the 60s and asked, can we characterize such graphs? So this seems at the moment quite hopeless to give a full description. But actually, I want to respect the analysis. So, okay, so these are the graphs that I want to investigate. They're geodetic. They're 2 connected. So this is to kill Avi's example of the tree. Why do I want to assume 2 connectedness? Because if you have a graph like this, then really understanding whether it's geodetic, this has to be geodetic, this has to be geodetic, and going from here to here, simply go to the one cross point. So this is uninteresting. So that's really, you're not losing no generality here. But I also want, this is losing generality, but rather than saying that loses generality, it focuses us. I want to assume that all degrees, all degrees, are at least 3. And this, I think, makes the problem much more geometric and combinatorial, because if you replace an edge by a path, then it becomes much more arithmetical. Can this number plus this number minus this number be bigger than that, or something like that? Which is definitely interesting, but I think for me that's the core of the problem. And I think this is a very, so will it be for if I really go over 60 minutes? No. I'm just trying to, what I should throw to the sides of the. Okay, everyone will go.
Fine, but we have to go to lunch before they close.
Okay, good. Okay, good. Okay, so I'm telling you. No, the trouble is, of course, I'm telling you now, and then at the end I say, but I didn't tell them X and Y and Z. Too bad. Why did I tell them all the stories at the beginning? Okay. Okay, so I think that's quite a limited class of graphs, and of course there is clicks also, another an interesting example. So let me tell you one family of such graphs.
Are there Kelly graphs that are geodetic? Other interesting Kelly graphs?
I don't know, and my belief is that no. But you'll see. I will say my beliefs very clearly. Don't worry. So reasonable construction. This was never in a journal. I hope I'm pronouncing the name correctly. I think it's 78. If I don't, that's in a thesis. He made the following nice construction. So this it satisfies all of those, and it has diameter 4. So you start from the point line graph. That's another one of the repertoire, the golden repertoire of graph theory, point line graph of finite projective plane. So there are the lines of the projective plane here, there are the points, and there is an edge if this point is on this line. And it has all sorts of wonderful properties. And so this is a cousin of this. This is by no means geodetic. So instead, what he does, so that's a very standard object that we use the whole time for lots and lots of things. So instead, he puts here flags. So what's a flag? So this line looks at all the vertices that it has, and you create a clique. So this is comprised. So this line is L, and this clique is comprised of all the L and P, of L and all the P that are in L. So you turn this into a clique. And the point P is every point is going to be adjacent to this. Now it's not even a very tiring exercise. You can check that this has these two properties.
Okay. So it has many more points on the top.
That's correct. Okay. That's correct. And then you just check. There is really because of the symmetry of this, you have to go point to point. Point to line on which it lies, point to line on which it doesn't. And there's not so many 4 or 5 cases to check and verify that that's it. The path is unique. And okay. And in fact, so this already brought me to the question.
Right, so the flag is the click that is there. You think about it as an.
It's a click. It's a click. So
it's just a click without faces. It's just a.
It's a click. It's a. I mean, we're just graph. We're not doing. We're not doing any complexes or anything. Just a graph. So it's all these vertices form a click. Plus, in my conversation with the student, we call it a porcupine. It's So there's a porcupine. Every click like this, plus the edges that connect this to all the vertices that are. So you check, it's not difficult. And so I was asking myself, can the diameter be bigger?
And the student found it, actually, unfortunately, we found it mentioned somewhere, so he didn't write it in the paper. So let me,
Or maybe you want to say if John worked with, I already forgot his name. Yeah.
Sisma?
Yes.
No, it's coming up. No, it's
You're not there,
different.
you're not
No,
there.
we're not there yet. No. So this is with the student Asaf at Brown. So what Asaf discovered, but as I said, it was known before him too, that if instead of working with a projective plane, you work with an affine plane, to do this the exact same thing, then the diameter is 5. And one more thing, which is completely his, he proved, so with Asaf, we proved that such a graph is actually 3 connected. That's interesting, quite non-trivial. So if you're assuming you're 2 connected, you already get 3 connected. So this is weird. Now, but here's my, I don't know if to ask it as a, but yeah, let's, I think people get more excited if they can infute conjecture. So let me state it as a conjecture. Conjecture, the diameter of such graphs is bounded.
Yeah, that's the graph.
So if a graph is geodetic,
Yeah.
2 connected and all degrees are at least 3, it cannot have, I don't know, diameter 100. Which implies, by the way, automatically the same statement, not doing the same number on the girth, right? Because the diameter is always half the girth. So the same thing, I could also, the weaker conjecture would be, okay. I don't know. But it seems that this is, I can tell you various other things that, okay. Asaf sought quite seriously such graphs, and he said he didn't come across a single such guy of diameter 3. Do they exist? Don't they? No idea. Okay, so now I really come to the main topic of my talk.
Now an attempt to find the diameter for one with a computer is probably not that hard by some kind of exhaustive.
Not so sure. Not so sure. They are very rare. That's for certain. They are very rare. If you just do brute force search, I don't think.
How many vertices?
Well, you cannot have too many because
Yeah.
otherwise the diameter will have.
Yeah.
If the power- well,
So I don't know. This I'm just telling you that Asaf tried quite a bit on the computer and he didn't find a single example with diameter 3. But this he told me, so I don't have any first-hand.
Wait, so the number of vertices is bounded as well?
No, the degree is at least 2.
No, but if the diameter will be 3, then the degree, well, it depends.
No, but say that the conjecture is true, that the diameter is bounded, not 3, but say we're the largest diameter. So does it imply immediately that the number of vertices would be bounded as well?
I don't
Because the
see.
degree can be high.
Yeah.
You can have, I don't know, graph of diameter of degree proportional to n. And
But
just-
can have graphs, of course. The question is, doesn't the geodesic somehow prevents you from stacking more and more?
apparently, yes, but this is to me, we had to sweat quite a lot even to prove something like this. They're still mysterious. Very, they're very hard to catch, these creatures. You were saying?
So if the conjecture is true, that when I take a graph and I look for like the densest geodesic subgraph, it should be tree-like, like either not too
No,
connected.
they
or-
don't have, no, you see, these things, of course, you can start to quantify. And that's certainly interesting, and some attempts in these directions were made. You want to say, okay, so there, you back up from the definition and you say there are not too many. That's certainly interesting. A little bit is known about this, but not much. But let's come to the bones of things. That's, I think, the most bone-like definition here. But I don't know if
understanding correctly what you're.
I was trying to develop intuition about geodesic graphs, and so I was taking an arbitrary graph and looking for the densest geodetic subgraph.
Most likely it would have none.
Well,
You know,
it's fine.
it will have a clique.
Exactly.
No, but you want induced or non-induced?
Oh, okay.
All these things are certain, but it's quite amazing. So perhaps, I don't know if any one of you had heard the name Ore before, but he, graph theorist,
Lots of other things.
of course, he was also a
But
major
not
figure
commutative algebra.
in group theory. Yeah. So, yeah, he was something, and so he was a major figure. It wasn't somebody, from someplace, and still, didn't attract, and I think these are very interesting. Okay, so now we come to the main part of my story. This is mostly work with my student Daniel Sisman. And let me, okay. So again, let's start with the same thing. We have a graph, but now so again, we have a graph, and we have some length or weights to the edges. And let me, so I will not all the time tell you precisely what, I mean, if you ask, I'll tell, but most of the time I'm going to ignore the possibility of equality. Okay, so now if these numbers are generic, then there's this aspect of unique shortest path is given. Okay, so mostly I'm going to be talking in this about this, and perhaps occasionally we need to be more careful with it.
So you want to say that with weights you will have a unique. Everything will be geodesic. Yeah.
Absolutely, every pair there is a unique shortest path. Okay, so this gives you a path system. Path system means that for every U and V, there is this path UV connected, shortest path. And I put it in parentheses on purpose because now I want to point out something completely different. This is okay. You saw this and it's gone. Okay, so I got confused. So we say we call consistent, the big part, okay, consistent if it's called undertaking subpath. What does this mean? This means that if the path from U to V goes via X and Y, then this part of the path is PX1. So now this is the main definition of the which to. So forget now, the weights will come back, but
the path system is not there exists, it's given.
It's
the
given.
Path system
So
is a collection of paths.
the path system is a collection of paths, and it's called consistent if it's called undertaking subpath.
So if it was shortest and we didn't erase it, it would consist by the
Right, which brings me to the question that starts. So pushing up and pushing down. There are two separate phenomena. I have another one.
But this doesn't.
This one is
so.
Okay.
Actually, it's very good.
Okay.
Okay, so the first question that Daniel and I ask ourselves, is every consistent path system graph coming from the weight system.
From the shortest path of
Not to
subway.
keep in suspense, the answer is no.
But that's the question, is does it come from the shortest path?
Yeah. Isn't necessarily, give you a consistent path system, can you always find length to the edges that will yield this as the shortest path system of corresponding to W. Okay, so I have to the picture. So remember, I told you that this graph, every two vertices have either an edge between them or a unique two-hop path connecting them. So I'm going to show you a consistent path system, which does not come from any weight system. So what is it? Mostly, I'm going to do the obvious thing. Two vertices which are adjacent, I use the edge between. Two vertices which are not adjacent, most, except for 5 pairs, which I'll show you momentarily, there is a unique common neighbor and you go through it. There are 5 exceptions. The exceptions are that if I want to go from here to here, I go like this. I take a 3-hop path rather than the options to go there.
And you do it cyclically.
And I take this one and I rotate it now 5 times. Okay, so except for these 5 exceptions, I do the obvious thing. So suppose that this came from some weight system. So let's say this is W1, W2, W3. I just, of course, I have to give weights to all of them, but if this is really what happens here, then I have the inequality which says all WIs are positive. So all I WI is positive, and I have this one would say that WI plus W2 plus W3 is, let's say, less than or equal W4 plus W5. But now you write these 5 inequalities, you add them all up, and you find out that the edges in the center are non-positive. Okay, so that's a proof. So first of all, let's introduce some terminology. A graph for which the answer to this question is yes or no is called replaceable and non-replaceable perspective.
I think.
Yes.
If you can't you do it on an odd cycle just to say if 2 are almost antipodal, then you take the slightly longer path?
Such a great question. You will get the full answer to your question soon. The answer is no, and then you'll get it. And I'll tell you much more than you've asked. Okay, good. So with this, so this proof is it really tells you something. Non-realizable. So I refer to this also, it's property of the graph, but also property of the path system. So a path system that shows that the answer is no, I call it non-realizable. Okay, so a non-realizable for given non-realizable consistent there exists a short proof of non-realizability. Oh, like this. But in fact, so this is a linear program. And
Can you explain what do you mean by a short point of?
something really like this. So there is a collection of inequalities, plus I can tell you coefficients, and now I'm shoving other, sliding in the LP duality, linear programming duality, which is really a very fundamental, that easy fact. I can, here, all I have to do is to add them all up. And the LP duality says that if you have a system like this, which is non-satisfiable, there are some coefficients that you can multiply and will show you that 0 is bigger than 0, or some W is non-positive. Okay, good. In fact, something stronger is true, which I don't want to really do.
This is the short, I'm just trying to understand what is the short point of.
Short proof. Short proof.
Proof.
Ah, proof.
Sorry.
Okay.
Sorry. So, in fact, something, okay, so I'll say one more thing about this. A priori, if I give you the graph and I give you the path system, then you can write, it's obvious, I could compare this path with any other path that connects these two guys, and I would in principle have to write all these inequalities, which in general is exponentially large. But using standard trickery of, this is going back to work from the 80s of Gretsch, Lobas, and Schreiber, which had huge influence on how to use the ellipsoid algorithm for linear programming to deal with things. This can all be done in polynomial time. Okay, so given a path system, a consistent path system, it is possible to write a short proof, and I'll say more about this. Not only short, but really humanly verifiable. So now let me jump a little ahead of myself. We've used in this paper computers in a very substantial way. Luckily, Daniel is not only a very strong mathematician, but also a great programmer. So we have used this skill as a programmer. So there are various graphs, I will come to them soon, for which he found a non-realizable, consistent path system. He solved the linear program. And the point is, could we have done it without a computer? Possibly, but most likely no. But the nice thing, we have this expression in Hebrew, learning things through, this comes from the military, through your legs or through your feet. And I felt that it's for the first time that I felt through my feet, P versus NP. So the computer found these proofs, but now in the paper they're written in such a way that a normal human being can easily verify that this is non-realizable. So there's a system of inequalities that you can check. They really say that this path is shorter than some alternative, and some coefficients to multiply, and then you check that this has proven to you that some W is non-positive. So it's really interesting for me, and I'll tell you in a minute more. My perspectives as a theoretical computer scientist have expanded from this experience. It's really, it's not just some strange idea of theoretical computer science. This business of verifiability is real. It's not. And I hope to get to this. There is one exception. All the paper is completely verifiable by humans, except for one thing, which is, we'll get to. One example, which very strange. Okay. Good, so let me tell you the theorem now. I will also say, okay, theorem. I'm writing it like this because the first version that I will write is not going to be pure, completely mathematical. So this is the part that is not so good, but I'll make it absolutely precise soon. The vast majority of all graphs, so there are three parts. The vast majority of all graphs are non-realizable. So this example that we saw with Pettersen graph is not the exception. That's the rule. That's not the exception. Two, the outer planar graphs. I'll tell you if you remember what that means. Replaceable. And three, Feasibility. Here too, I learned the lesson, so I want to share it with you. Okay, so let me. It's like in a rotting house, right? I have to fill now all the little cracks that I made. I will do this one by one. So at the end, it will be a solid mathematical state. So number one, I can tell in more than one way. It's not that we haven't really characterized them, but e.g. for number one,
you must find some combinatorial property that implies that.
Exactly. That is,
and then say most graphs are like.
Right, and I can say I can have more than one such property. Yeah. Just to illustrate, e.g. for one, if G is two connected, its least degree or degrees with these three and has at least 13 vertices, then it's the okay. So exactly as Avi said, I can replace this by other conditions that most graphs in a very strong sense satisfy. Okay, so I filled in the crack for number one. For number two, I think I mostly have to make sure that you all know what outer planar means.
Nati, I believe this would probably answer the question, but is there some implication between metrizeability and geodetic?
No, not in any direct way that I know. We were inspired by this. You know, I started, I told the student about this question, we started talking, then this became the master's thesis of Asaf, and with Daniel, we went to, he's a PhD student, so we went to but no, not in a direct way that I know. But,
like geodetic, which is non-metrizability, or geodetic, which is like.
I didn't check that. That's a good question. I haven't checked it. Interesting. Okay, good. Thank you. Okay, so outer planar, that's a standard definition in graph theory. So G is outer planar. If it can be drawn in the plane such that vertices are on the outside face. So something like this. And you start putting all sorts of things like this. That's outer planar. In particular, cycle is outer planar. And I don't know if I will, but this is a proof that I'll describe. So this was the first step in proving this theorem, showing it for a cycle, which is, okay, let me say one thing. This is a paper that I really like and lots of, but it's not going to win any beauty contest. It's maybe a lot of hard work, in the minds.
You have an example of a planar graph which is not metrifiable?
Yes. So yeah. Actually, this goes into the proof. Yeah, we will see it. Yeah, we will see it, and then you will also get extra. You will get an answer for this plus. Okay, so before, okay, let me don't want to forget this question. Number 3. That's a correct mathematical statement. I don't have to tell you anything in addition, but I have to be honest with you. I have no idea what the algorithm looks like. I will explain. There is a finite list of graphs we'll come to, which I know is finite. I know some of its members. I have no way to start even. Does it have 20 graphs? In which case, people can understand it, or 20 to the 20 to the 20 times. And what these graphs are, absolutely no idea. I don't think it's hopeless, by the way. It's
but the algorithm tests if there are subgraphs of your graph.
Yeah, there are topological minors. We'll come to this. But let me, okay. So one thing that I think at this point, graph theorists would ask me is when metrifiability closed under minors. So let me just to make sure that we're on the same page. A minor is a graph, you're starting from a graph, and I give you, you're allowed to do 2 things: remove edges and vertices, and contract edges. So for example, planar graphs. So do I have to tell the forbidden minor theorem?
Yeah, it's a good idea to tell the forbidden.
So I'll tell the forbidden minor theorem. This is really,
they earned it.
This is really,
Yeah, I mean, who doesn't know the forbidden minor theorem? Okay.
Okay, then I should tell you. Then yeah, okay. There is right in the Greek academy, there was a sign: if you don't know geometry, don't pass this. So if you don't know what the forbidden, what the minor theorem, forbidden minor theorem is, don't leave this room. I will. Okay, I'll make sure. Okay, so you understand what minor means. Okay, so first of all, I'm going to answer Avi's question, and this is, as I said, the one case. The one piece of that I don't know how humans, if my life depended on it, I could have done, but you should really point a big gun to my head for me to do this. So here's the example. Yeah. So this graph. So this graph is metrifiable. This is metrifiable. And if I contract this edge, then I come to this graph. This one is not metrifiable. Okay. So here you understand by now, I think, how I prove it. I find some, we have it in the paper, we have some, you write down some consistent path system, you write the system of inequalities, you convert it. This is metrifiable. And this is really the part. So, if usually or often when you prove that something is in P, for some of the bigger achievements of this sort, let's say linear programming. We knew, or people knew beforehand that linear programming is in NP. I can show you that the linear function can attain such and such value, that it's in coin P because of linear programming duality. I can give you a bound that you can check. So P being in NP intersect coin P is often, in serious algorithmic problems, it's often a step or a situation that we are at before we can prove that something is in P. And here there is something really very, very confusing. So let's even understand this. So being non-realizable, I think by now you understand. This is very easy to verify proofs of this. Replaceability is still, to me, completely mysterious. So in particular, if you're looking at this particular guy, I want to show you the only way that I know how to prove or how to convince that this is replaceable is the stupid way that we've done it with Daniel. He tested, this is still small enough, you could still test all, even this is not entirely trivial, but I think I'll have time to tell you how that is done. You can test all the consistent path systems, and for each one, prove that it is bilinear. Now apply linear programming and say that the system is consistent. But replaceability, really the mysterious part, which I don't understand, and by the way, Abby, so there's your non-realizable planar graph. This is still the part that I completely do not understand. And so a popular sport among combinatorialists is to find the most humiliating version of the problem. So I, member of this proud club. So let me show you. This is really amazing. That's very, very typical of the subject. There is a graph theta ABC. Theta ABC is this graph. This is length A, this is length B, and this is length C. So if the numbers are big, I don't remember the figures in the paper. If the numbers are big, then this is non-realizable. If the numbers are very small, then it is. There is a whole range in between that we don't know. What could be simpler than this? It's embarrassing, right? So I'm embarrassing myself. We don't know the answer.
Can you explain what would be the counter the non-realizable path system here?
I don't remember it, but it's in the pen. So let me not try to create it on the spot, but they exist. We've proven it. You should look it up. I don't remember the exact figures, so I won't try to recreate them on the spot. Okay, so Avi, I should really work out my time. So I can
finish by 12:30.
Okay. 12:30. No, 12:30. No, 12:30. I should be fine, and I won't have to feel having told all sorts of nice and interesting things. Okay, so let's do this. Okay, so let me. So what do I want to do? I will just erase the theorem. Good. Yeah. So let me write it very quickly. Most graphs are non-realizable. Autoplanar R. And replaceability is these are the three parts. Okay, so let me explain how this proof works. So we already saw. That's I still owe you something. Right. So we'll see about 11:30. No, we will leave at 11:30, but perhaps other things will not be told. I tend to tell stories like this. I start the story, then there's a side story, then the side, which is fine, but not in lectures always, because
Perhaps I've left something. Let's do the forbidden minus one. This is really one of the, to me, I think this is one of the greatest, not of just of combinatorics, of modern mathematics. It's really an amazing theorem. Okay, so let me state the theorem first. This is a series of 24 papers, about 40-50 pages each. Not an easy read, none of them. So the first one or two I tried to read and I decided, okay, I have other things to do in life, I will not try. Which proves the following theorem, but you see, here is enough space to write the theorem. That's not usually the case. Any non-trivial minor closed family of graphs is finitely many obstructions. Then we made it to the
Obstructions are forbidden minor.
What?
Obstruction.
No, I'm going to explain. Still, there are words to. Okay. First of all, it's very good to start from an example. Good example, which really has been the motivation for much of this. This was, by the way, conjectured by Wagner in the 30s. It's planar graphs. Planar graphs are, this is obviously a minor, by the way, non-trivial means that it's not empty or not containing all the graphs. Planar graphs are closed under minor, removing an edge is obvious, and contracting, in higher math language is just homotopics. You understand. But the theorem, so
Has two forbidden.
planarity was characterized first by Kuratowski in the 30s, and later Wagner. In fact, you know what? Let me take a second because this will connect to. This was a huge breakthrough by Kuratowski in the 30s. I'm still not in, but you'll see in a moment. The graph is planar if and only neither K5. So that's the complete graph on 5 vertices. No K3 are the topological minors of it. I'll leave this, we will return to explain exactly what this means. And what Wagner did is this thing. Okay. So let's okay, so K5 is non-plane. K3 is non-plane. And in principle, you could think of, there is a list of perhaps infinite, a priori infinite, of all the graphs which are non-planar, but once you take a minor of them, they become planar. From there on, if you keep minoring them, they will stay. So there is such a list. There is nothing, here I'm saying something completely trivial. The big thing is that there are a finite number, in this case, even just 2. Okay? And what this amazing theorem says is that this has nothing to do with planarity. It's for every minor closed family. Okay. So now you know. Now if they come to take your car, you can go. Otherwise, not leaving the room without knowing the forbidden minor theory. Okay, so now let me also.
Can you just tell one other family where this is useful?
Yes. First of all, you are right that this is not huge, unfortunately. I don't think there has been. No, it's an accomplishment. Okay.
And take any surface and say.
No, that's perhaps too cheap. What Avi says is correct,
It's
but
just cheap, but you can take any surface and say, all the graphs are
yeah,
embeddable.
but
and
perhaps,
stuff.
but
But
perhaps,
probably there is a simpler proof.
Well,
It's not so simple.
it's not
no.
that easy.
No, it's
Yeah.
not.
no,
I like
it
it.
was, I don't think it
That's
was.
probably took,
Yeah.
one paper.
Perhaps, I'm not entirely sure, but perhaps somehow I remember two numbers, 35 and 103. So I think one of them is for the torus. This was
Yeah,
perhaps known
I think so.
before.
I think it's
And one
30
for the
something.
projective plane, right?
Yeah, I remember Torres is 30 something.
Okay, good. But here is another thing. There are graphs which, so every graph can be embedded in R3, right? You just throw the points at random and you connect them by an edge, by an interval. But some graphs are like this, that if you embed them in R3, then they will create a link. They will be two disjoint cycles which geometrically look like this. This is also,
Nice.
yeah.
The graphs that have a linkless embedded.
Yeah, exactly. Linklessly embeddable graphs. Mine is closed.
All sorts of embedding in stuff with topological.
Not only. Okay, there is.
When some
Well,
There's a beautiful theory. No, good thing that good thing that you're asking. Yeah, this is a very another. This was my first sentence. In how many ways geometry and graph theory interact? There's something very interesting, which although very strong people have worked on it and a good number of, I don't think this subject has been exhausted. There is what's called the Colin. I will not even try to Colin de Verbier. If I took your comment in the wide sense, it includes that, but it's really different. The Colin de Verbier parameter of graph. I will not even try to tell you what that is. But that's another domain where things like minors come into play. Yeah, okay. So now I should tell you what a topological minor is.
What's it's monotone under minors or something like that?
The Colin de Verbier,
Yeah.
it's minor closed. So when you're looking, there is this parameter.
The parameter is the largest dimension of the second eigenvalue.
Right, so you're defining this as mu of G. So all the graphs with mu of G less than something, less than or equal to something,
This is,
that's a minor closed.
and then, but, okay.
Okay, so what is what was the original result of Kuratowski's science? Well, what's a topological minor? That you can find 5 vertices. Every two are connected by a path, and those paths are disjoint. So in other words, you're taking K5 and you're turning edges into paths. That's the definition of a topological minor. Okay, so the theorem that we prove, and much of what we've done lies in this.
Visibility is minor close.
Exactly, topological minor. So,
But you gave an example where you contracted an edge and it became non-realizability.
right, but that's minor. It's a minor and it's not a topological minor.
The topological minor is just adding.
Exactly. It's the graph, you find the subgraph. Okay, now let me perhaps, so it's an important thing. So I say that H is a topological minor of G if there exists a subgraph of G that is H with edges replaced by this joint path. So the major step is to show that replaceable graphs, are closed under topological.
So
Well, wasn't the theta ABC a counterexample? You said that you somehow add more and more dummy vertices and
no, on the contrary, the short ones are.
it's the other
The long ones are
direction.
not.
It suddenly becomes, I see.
Okay, good. So, yeah, so if you prove for some A, B, and C that this is non-realizable, then you can now increase the numbers and keep the second point. Okay. So just, a bird's eye description of the proof of fun. We prove this takes work. And then Daniel found on the computer, I think 10 or 12, I forget, specific examples, which so let me repeat. He examined all consistent path systems in these graphs and found that they are non-realizable. And later we showed that every rich enough, at least certain vertices, no vertices of degree 1 or 2, contains one of them as a topological map. Then that's hard, not very inspiring work, but we've done it. So therefore, that's how we prove number one. Okay, let me still have a few minutes energy. You're still good. No one's going to sleep. So, but, sitting to sleep. Good. So, you are right. Good question.
So maybe before this, I mean, this theorem implies that testing a graph, which is minor close to be in the family, to have the property is in P. Right, because there are only finitely many subgraphs you should check. I mean,
No, wait, Avi. I think your complaint, you have a strong complaint to make. Let me help you. There is no
topological.
Yeah, there is no the theorem, this great theorem. There is no such theorem for topological map. But we have enough structure in our problem. So, for example, it suffices to deal with graphs in which at most 13 vertices or 12, or actually 8, but forget it, it's not important, vertices of degree at least 3. So this imposes structure enough. So such a restricted value does satisfy a finiteness theorem. But I have no idea how big they are. I don't consider it hopeless. At the moment, I don't understand. Okay, so should I continue with this? I promise what I'm doing now to. Okay, so in the hope that he's coming better, I'll tell you something else.
But just to
Oh,
Yeah. Well, then
no, he said you have to go if they call him for.
No, he said that I'll give him 2 minutes to. If not, I'll tell you something. I'm not going to go. I hope. I'll tell you something else in a minute. Go ahead.
So just what you just said to Avi means that meterizable have finitely many obstructions?
Yes.
Okay.
Yes. And this is, and again, by theorem of Robertson and Seymour, you can check if a graph is a topological, efficiently check if a given graph is a topological minor of another. So I give you a list, it's a finite list, you check of them and all of them, and then that's your algorithm. But
Yeah.
As a mathematician, I'm done. As a human being, okay, good. So good. So let me tell you. Should we disappear? No? So let me tell you. I have still 2 stories to tell you, and I'm deliberating with myself. So if your name, I can. Okay. Okay, you're telling me Flash. Okay, good. He's not going to miss lunch. Okay, so good. So
the algorithm that checks if a given graph is a topological minor of another graph, is it complicated?
what do you expect? Of course, very complicated.
Okay, it's not something they can do in parallel or stuff like that.
Look, some of these things. This is part of a whole field, which, they started the field.
Very much at work on this.
At work on yeah, and understanding these things, the algorithmic aspects of this. Okay, so a few words on improving the cycles, and with this I think I will stop. So that I don't create hunger in Princeton. Okay. Okay, so let's come back to the original definition. The original definition, what a consistent path system is, you understand, but an equivalently, a consistent path system is completely equivalent to a consistent tree system. And what's a consistent system? We have a graph. Move a tree at every vertex. And consistency means, so there is, you have one spanning tree for each vertex. And consistency means the UV paths in TU and in PV are identical. And it's very easy to see how do you do this.
At the UV.
First of all, that's a concept, and I'm saying that the two things are equivalent, and that's very easy. To create the tree system from the path system, you just look at all the chosen path to U, let's say, root of the two, and consistency just implies that this is a tree, and from the trees you want to know the path between U and V. It's the path that both them occur in the tree. Okay, so now let's look at the cycle. So the cycle, the tree is just remove an edge.
So you want to prove that it's methodical?
I not a full proof, just to indicate the main steps. And you know, the outer planars, there is more work to do. So what does it mean? It means this. So who's the tree of this guy? So all I have to tell you is which edge to throw away. So a tree system, not even a consistent one, is simply a mapping of the cycle in the cycle from vertices to edges. Now we can prove that that's not difficult at all. This is not our proof. This is really, you know, when I give talks about this and I insist on proving something, this is what I would usually prove. So this is something that takes a few minutes and you know, can be presented in decent public. Okay. So you can show, and that's not difficult, that consistency means that it's crossing. So which means if he chooses this and he chooses that, then these two arrows must cross.
What's the mapping between the vertex and the...
So the meaning is that the tree corresponding to this guy is the cycle minus this edge.
I see.
Okay. So, and then...
So the mapping in general is choosing the what's outside the tree.
Exactly.
The first Betty number of edges outside the tree.
Exactly. Okay, so who's and for consistency is equivalent with being crossing. And now what could happen is, so it's still possible that, let's say, all these three, all this slide, this is still considered crossing. And what you show is that when you take these, we call them persistent edges, and you contract them, then
what you get is precisely the standard, your first example, the odd cycle. So this, in every consistent path system on the cycle, when you've contracted the persistent edges, you'll wind up with an odd cycle with a standard metric. I think that's a good point to start. Thank you very much.
Questions, more questions.
What do you ask me? People from Zoom.
Anybody from the Zoom? Okay. Okay, we'll ask you at lunch more questions. Thanks.
Great.
Thank you.